This is homework 4, part B. So to start, we can model our Stephen-Maxwell equation by saying that our driving force is equal to our vapor component I divided by, or the change in that vapor component divided by the change in position, which is equal to the summation of J of our vapor component Y times our total flux J minus our vapor component J times our total flux I divided by our concentration times our Stephen-Maxwell diffusion coefficient of Ij. So we'll start with acetone, acetone. So if we can imagine we have acetone and methanol going up and our air going down. So our acetone I equals 1 will look something like this. So we'll say our Y1 N1 minus Y1 N1 over C concentration divided by concentration times our Stephen-Maxwell diffusion coefficient. And then to that we will add Y1 N2 minus Y2 N1 and then same thing with our third component. So this term will go to 0 and we'll be left with this. Okay, so then we can do a similar thing with our acetone. Our methanol. Say acetone, methanol. Say this term will go to 0. And then we can rewrite our equation for the methanol as Y2 N1 minus Y1 N2 for our concentration times our coefficient plus the same thing for component 3. So we'll introduce a new variable here. So our scaling factor. Okay. Scaling factor, which is equal to say Z over delta. So we can rewrite our dz term, or we can rewrite this. We'll say z equals our scaling factor times delta, and we'll say that our dz is equal to our delta times the change in our scaling factor. So we can rewrite our equation. So we'll say, go back to acetone. We'll say our change is equal to our delta, or length of the pipe, times basically just what's up here. So y1 n2 minus y2 n1 divided by our concentration times our diffusion coefficient plus y1 n3 minus y3 n1 divided by our concentration times our diffusion coefficient. So we can simplify this by factoring it out. We'll find, we'll get, say, y1 times our boundary thickness, n2 divided by c times our diffusion coefficient minus y2 times the same thing. Say plus y1, same thing with n3. Oh. And then minus y3 now this term goes to 0 because our air doesn't have any flux because since it's going down here, it's being forced down. It's only reactive to the flux going up since it has nowhere to go down. So to solve for flux of our methanol, 2, we'll get C times our diffusion coefficient divided by our boundary thickness. So because this y1 term is going to be about 1, same with this. Oops. So we'll say we know our concentration is equal to our pressure divided by the gas constant times our temperature. So we can say that this is equal to our pressure times our diffusion coefficient divided by RT delta. So we have all these values. So for our pressure, we said pressure is 99.4 kilopascals. So 99.4 times 10 to the third pascals times our diffusion coefficient. We said 8.48 meters squared per second divided by our universal gas constant, 8.314, times our temperature of 548. Oh wait, 328.5 Kelvin. And then times the pipe length of 0.24 meters. So if you plug this in the calculator, we'll get something like 1 over 788. Okay, so here we are in Excel, and I have here written out some of the values that we need. So we have our mole fraction of our acetone, methanol, and nitrogen, and then we have our diffusive coefficients between our acetone and our methanol, our acetone and our nitrogen, and our methanol and our nitrogen. Then we have the pressure, our temperature, our gas constant, and then our concentration, which I said was equal to our pressure divided by our temperature times our gas constant. Temperature times our gas constant. And then we have our boundary thickness. It's hard to do with my left hand. Okay. So, to start this, we'll make 1,000 steps. So, go to fill, series, columns, stop at 1,000. And then those steps will divide our the thickness of our film by that number. So call that z's for the distance, and we'll say each z is equal to the value of the step times our length of divided by 1,000. And then we'll fill that down. If we scroll all the way down, you can see that at our final value will have the thickness. So this will just be at the end of the film. So, oops. Going back up to the top here. Okay. So we'll also look at how our mole fractions change. We'll have mole fraction of acetone, methanol, and nitrogen, and then we'll look at how our mole fraction changes with respect to our change in our scaling factor. So we'll put in our, let me define these names. So we're given the scaling factor at green slip. Okay, yeah. So we're given our mole fractions at the surface. So we'll say equals y1 dot equals y2 dot and equals y3 dot. So this will be for our acetone, and then we'll have one for our methanol too. And that change in our scaling factor is essentially just this length divided by 1,000. So what we'll have here is our formula that we found earlier. So we'll say our change in our concentration of acetone divided by our scaling factor is equal to our delta, so the boundary thickness, and that'll be multiplied by our mole fraction of our acetone times the before that actually. So we made estimates for our fluxes. So say the flux of our acetone we said was around 1 divided by 788. It'll be the same for the flux of our methanol. Oops. And then for air, the nitrogen we said again will be 0 because it's dependent only on our flux of methanol and acetone. So this will be our boundary thickness times our mole fraction of our acetone times the molar flux of our ethanol or our methanol, and then subtract from that the mole fraction of our methanol times our flux of acetone, and then we'll divide that by our concentration times our driving force, our diffusion coefficient between our acetone and our methanol. And then we'll add to that, make sure we're multiplying this throughout the entire equation. So we'll take the mole fraction of our acetone, G2, times the flux of our air, which we said was 0. So we get negative mole fraction of the air times our flux of acetone, and then we'll divide that by our concentration times our diffusion coefficient between our nitrogen and our acetone. All right, figure out the parentheses. Okay, and then essentially it'll be the same for our second one. So we'll say it's equal to our thickness times the mole fraction of methanol times the flux of acetone minus the mole fraction of acetone times the flux of methanol, And then that'll be divided by concentration times the diffusion coefficient. And we'll add the negative mole fraction of our nitrogen. Times the flux of our acetone, and divide that by our concentration times our diffusion coefficient. Okay, so for our change in our mole fractions, say it is equal to our previous mole fraction plus our change in our mole fraction with respect to our scaling factor, and then that'll be multiplied by our 0.24 divided by 1,000. So that's just our initial scaling factor. And that'll essentially be the same for the acetone, except it'll just be instead previous mole fraction of our acetone and our scaling factor for our acetone. And then for nitrogen, that'll just be 1 minus this minus our other two mole fractions. And bring this down for these two. And send the whole row down. We scroll down. So if we remember, our target mole fractions are going to be 0, 1, and 1 respectively. And 0, 0, and 1. And we could see that we do not have that. So G and H. What we'll need to do is use a solver to adjust our values for the fluxes. So if we take the sum squared of our two values, so we'll say we'll get the sum squared error. Oops. That's our sum squared error. And if we use that, so we want it, the closer that number is to 0, the more accurate our data will be. So if we go to formulas, data, solver, so we'll say our objective is to minimize this sum squared error. And in order to do that, we'll change our flux values because these were just guesses. We'll hit solve, and the computer will do its thing. Get our numbers here. And as you can see, the value is a lot closer to 0. And if we scroll down, our mole fractions of our ethanol and our methanol and our acetone are very close to 0, and our mole fraction of our nitrogen is super close to 1, which is exactly what we wanted at past our film thickness. So as we can see though, our initial guesses were pretty similar. We had pretty similar guesses for our fluxes using our Stephen-Maxwell equations. They have the same magnitude, and the reason that is because we could plug in our values that we were given to the equation, and with the same magnitude, we would get a similar magnitude for the answer.